Hello wonderful person, this is Anton, and today we're going to be delving into some of the most incredible discoveries coming out of James Webb Space Telescope in the last few months. Because once again, this telescope has been able to push the boundaries of our understanding when it comes to early universe. And here, these observations are so unexpected that they're forcing astrophysicists to reconsider certain models when it comes to the formation of early galaxies and early black holes. And so let's discuss some of these recent discoveries in a little bit more detail and discuss why this is important and what's most likely going to happen next. And as always, you can find all of the studies relevant to this in the description below. But first, let's talk about why this is important and what exactly these new observations are trying to reshape. Now, for years, our understanding of early universe, specifically of the period known as the cosmic dawn, has mostly been shaped by theoretical predictions and only some observations from telescopes like the Hubble. And pretty much all of these early observations and predictions painted a picture of a gradual emergence of stars and galaxies that seems to have happened in the first 400 million years. But the observations from JWST pretty much started to change most of this as soon as it began its operations. And it pretty quickly became very clear that the universe was way more active and way more chaotic in these first millions of years following the Big Bang. Now here we obviously have to understand the concept of redshift. This is essentially the cosmological concept used when studying the ancient universe. As the universe expands and as the light from distant objects gets stretched to longer and longer wavelengths, the objects get higher redshift, with some of the most distant objects discovered by the Hubble Space Telescope essentially having the redshift of 11, although technically the highest spectroscopically confirmed galaxy was only at the redshift of 9. This would be approximately 600 million years following the Big Bang. But because the James Webb Space Telescope was specifically designed to observe infrared light that would represent ultraviolet light redshifted to be infrared, here it was very good at detecting luminous galaxies much farther away, with at least several galaxies now confirmed to be at a redshift of 14, or approximately 300 million years earlier. The most distant detection is approximately 280 million years following the Big Bang. But even these detections presented us with significant challenges. Here the suggestion was that there were just too many massive galaxies forming too early, and there seemed to be a little bit too many luminous sources that were just a little bit difficult to explain. And that's because, as I previously mentioned, a lot of this was based on theoretical predictions, with many of these predictions suggesting that it should be relatively difficult for stars and galaxies to form so quickly. And that's because the gas in the early universe is supposed to be super hot, and that would make it much more difficult for stars to collapse into dense enough objects to become stars in such a short time frame. Yet as far back as a year ago in 2024, we definitely had several confirmations of extremely distant galaxies at a redshift of at least 14. This was confirmed by several independent observers, so it was very difficult to argue with this. But now we have something even more incredible just a year after. This new study by Perez Gonzalez and his colleagues utilized some of the deepest JWST observations, mostly from the MIDIS and NG-Deep surveys. These are surveys designed specifically for deep extragalactic exploration. Not like Star Trek style exploration, we're just talking about looking at things. And these new observations were able to achieve extremely accurate results, identifying 9 new candidates. Candidates with 5 sigma detection, suggesting that they're almost certainly there, but candidates that seem to have a dramatic drop-off in certain infrared frequencies. You can actually see this visualized right here, because one of these objects is only visible in certain wavelengths, but not in other wavelengths. And that implies an extremely high redshift. For 6 of these objects, they seem to have an F200W drop-off, which indicates the redshift of approximately 17. That's about 200 million years following the Big Bang, and at least 80 million years younger than previous detections. But the biggest shocker was the 3 other detections that seem to have an even higher dropout, consistent with a redshift of possibly around 25. That's just 100 million years following the Big Bang, making this the youngest and the most distant object ever observed. And that by itself is super extraordinary. Nothing that far has ever been seen before. Although here we have to, I guess, mention a really important side note. Right now these observations are only based on redshift, estimated based on what we see in different filters. This is not an exact distance, and the exact distance can only be determined through additional observations by actually seeing specific elements inside these objects, such as for example hydrogen and helium, and by then seeing the redshift in the absorption lines of those elements only. And so at the moment this is still a preliminary distance, but nevertheless this is still very exciting. Exciting because we also get to estimate some of the properties of these ultra-high redshift candidates. For example, here we can estimate their mass. They seem to have around 10 to the power of 7 solar masses, with the estimate based on the mass weight suggesting that they're approximately 30 million years old. So these are very massive but also very young objects. They also seem to contain a relatively low amount of dust. And based on the observations of ultraviolet emissions from these objects, researchers think that this points at young metal-poor population 3 stars, or possibly some other powerful objects with a lot of ionizing radiation. But more importantly, when it comes to the actual shape, here there seems to be a kind of a mix, with some candidates appearing compact and point-like, and a radius of approximately 180 light-years, while others are at least 2 to 5 times larger, up to about 700 light-years across, and seem to be more extended. And this morphological diversity is quite important when considering different explanations for their apparent luminosity. We'll discuss this in a second. But importantly, there also seems to be a kind of a relationship when it comes to distance versus luminosity density. Here, the observed number of density inside galaxies seems to dramatically increase with distance. And so at a redshift of 17, the overall density inside galaxies is 4 times smaller than at a redshift of 12. Whereas the most distant objects at the redshift of 25 seem to have 25 times less density compared to much closer galaxies at redshift of 12, suggesting that these are extremely young, primitive objects, much smaller in size and much less massive compared to what was observed in 2024 and in 2023. But this rapid buildup of stars does present us with a bit of a challenge, mostly a challenge when it comes to galactic formation. And specifically because of the hypothetical dark matter that's supposed to guide the formation of galaxies early on. It basically means that a lot of these halos would have to be way more efficient at converting baryons into stars and more effective at forming dense complex structures very early on. Or alternatively, maybe these early stars were actually just much more effective at producing energy and light. Maybe they had much higher emissivity, producing way more UV photons per stellar mass. That would explain why they're so easily visible, but it would not explain why they're producing more energy. Although because we've never seen these primordial stars or population 3 stars, we obviously know nothing about them. However, a separate study does provide us with maybe one alternative explanation. What if these are not really galaxies and not really stars, but instead, as the study by Materi and colleagues explain, because of this outrageously high number densities, and obviously extremely far away distances, what if what we're seeing are primordial black holes? As a matter of fact, in this study, researchers go through a lot of detail trying to essentially explain how this cannot be galaxies or stars, and how it seems to be virtually impossible to reconcile with current galaxy formation model predictions simply based on this being stars. And so the proposal here is that the implied ultraviolet luminosity could be explained by primordial black holes, hypothesized to have formed in the first few seconds following the Big Bang itself. And the idea is that these primordial black holes, or PBH, with masses in tens of thousands of solar masses, would probably reside in low-mass dark matter halos and accrete surrounding gas extremely fast. They would essentially represent a kind of a collapse point for a lot of gas densities that were circulating in the early universe. And as these black holes started to collapse, and as the accretion disk around them started to emit light, it would start producing the effects we're observing. And so in this scenario, for redshifts greater than 15, all of this ultraviolet luminosity would be mostly dominated by emissions from these super early, super young primordial black holes, which is what we're seeing, and not light coming from stars. Essentially, they're suggesting, just like the models predicted, stars did not exist yet. And intriguingly, in this model, or in this hypothesis, there seems to be some support based on the observations. For instance, point-like morphology for some of these objects. They're just a little bit too small to be early galaxies or even early clusters, but would be much easier to explain if these were black holes. The overall emissions coming from these sources seem to be just a little bit too similar to what we usually see from central black holes in a lot of different galaxies. But more importantly, the overall mass and the overall number of these objects seems to be directly consistent with predictive models that previously suggested the existence of these primordial black holes. And if this hypothesis is correct, it would obviously have profound implications on cosmology. First of all, it would strongly disfavor stellar origins for the seeds of black holes, suggesting that black holes do not need stars to form. They just need a lot of mass, in just the right amount, to directly collapse and become black holes right away. On top of this, it would also suggest that many of these primordial black holes potentially served as initial seeds for supermassive black holes that start to appear all over the place just a few 100 million years afterwards. In other words, what we might be seeing here are sort of like these super early baby black holes that are going to be growing larger and larger, eventually reaching colossal sizes. But once again, at least for now, this is all very speculative. Here we need spectroscopic confirmations using some kind of a elemental observation from JWST in order to definitively establish redshifts and in order to confirm that this is exactly what they are. For example, in this case, if we actually only find hydrogen, and it seems to be as far away as initially claimed, in that case, it potentially is black holes and is extremely unlikely to be stars. Mostly because for stars we do expect to see something else, like for example carbon, oxygen and lithium. And so for now at least, we don't really know if this is some kind of a young stellar population produced through means we're not able to explain, or some kind of a really early accreting black hole that would confirm the existence of primordial black holes. Either way, what is certain is that many of these new observations from the James Webb seem to continuously change cosmological preconception about those few 100 million years following the Big Bang that constitute the cosmic dawn. And that's because so many unusual luminous objects have already been discovered, and many of them are just kind of difficult to explain. And so this early period, 100 to 350 million years after the Big Bang, marks a bizarre rise of very strange objects that seem to be bright enough and powerful enough to be visible billions and billions of light years away. Right now, the only thing we can see for sure is that the early universe might have been a diverse and active place, potentially containing both black holes and early stellar populations, but with somewhat different properties to what we have in a much older universe. Or at least that's the assumption for now. Honestly, at this point, I don't think anybody can answer these questions yet. And so, as I mentioned before, the next crucial step is to obtain spectroscopic observations. And so once we have these specific emission lines from, for example, hydrogen, or potentially some other signals coming from these objects, we can possibly come to certain conclusions. But I guess what's crazy about these observations is that this is actually pushing the JWST's limit to its maximum. By design, the telescope was supposed to observe things up to about a redshift of 30, or just under 100 million years following the Big Bang. And here we have these objects that seem to be just at that limit. But because these are still early discoveries, we have to be cautiously optimistic and acknowledge the possibility that maybe this is something else entirely, and maybe these objects are just much closer, and some of the data was misinterpreted early on. Either way, we'll definitely come back and discuss these discoveries a little bit more in the next few months, once there are some additional observations. Until then, check out some of the previous videos on similar topics in the description below. Thank you for watching, subscribe, come back tomorrow to learn something else, support this channel on Patreon where you can find additional videos without any ads, and can DM me directly, or by joining the channel membership that grants you early access. Or maybe by buying the Wonderful Person t-shirt with a JWST image as the centerpiece. Anyway, I'll see you tomorrow, stay wonderful, and as always, bye bye.